In this video, I'll be introducing you to derivatives. Now, derivatives are very important in calculus 1, 2, and even in 3. So, it's very important to have a solid foundation of derivatives before you move on. So, to begin, the derivative is just how a function changes over time, whether the function is increasing, whether it's decreasing. From earlier math, you might know this as the slope. It's no difference whether the graph is increasing, staying constant, or it's decreasing. Let's take a look at the graph. Now, in this function, if we were to walk along this graph, we'd see that we're going up. We're going uphill, so it has a positive slope or a positive derivative. In this case, we'd be walking downhill, so that means we have a negative derivative or a negative slope. Now, what about in this case? Are we going uphill or downhill? Well, honestly, we're doing neither of those things. It's constant. Everywhere along this function, the value is staying at 2. For example, at negative 100, the value is 2. Negative 50, it's at 2. At 100, it's 2. Everywhere, this value is 2. Looking at this next graph, the same holds for 7. At negative 100, it's at 7. Previously, it was at 2, but this is a complete different function. This is f of x equals to 7. So, everywhere along this graph will be equal to 7. Now look at this one. F of x equals 200. So we still have a horizontal line that's 200 everywhere. So because it's a horizontal line that's going neither uphill nor downhill, the derivative or the slope of this function is 0. So in our case with 2, in our case with 7, in our case with 200, the derivative is 0. I'll show you this in notation. Here we have f of x equals to 2. That means no matter what this x is, as it changes, whether it be negative 100 or negative 50 or 100, as we saw in the graph, the graph is always going to be at 2, which is going to give us that horizontal line that we saw earlier. So because it's a horizontal line, the derivative is going to be 0. For example, with this 7 as well. Remember, the 7 was higher than the 2, but it's still a horizontal line, so you get 0. In this example, where it's 100, it's still a horizontal line because you have no variable on this side of the equation. So, when you have no variable, and it's just a constant, a horizontal line, the derivative is always going to be 0. Now, let's go on to where we have a variable on the right side. A variable is just x, it's a placeholder. So, in this case, f of x equals 2x. The way this works is, this number is going to change, whether it's negative 1, whether it's 2, and then the right side will tell you what the number is for the function. And that will tell you how the graph will look. So in the case of f of x equals 2x, if I was to plug in 1 here, I would get 2 times 1 is 2. If I plugged in 2 here, I'd get 4 on this side. And I'll show you how that looks on the graph. On the graph, it looks just like this. See, at 1, the value is at 2. And for 2, 2 times 2 is 4. So when you have a graph like this, that's when you have an exponent. It's going to give you a slope. And in this case, I'm sorry, a variable. It's going to give you a slope. And in this case, it's an uphill climb. So you know your slope or your derivative is going to be positive. So now, how do you take the derivative of something like this? Well, this is probably the easiest one. If it's just an x with no exponent, you just cross off the x, and that's your derivative. So the derivative of 2x is going to be 2. If it's 7x, you just cross off this x, it's 7. If it's negative 9x, you just cross off the x, you get negative 9. If it's 1000x, you just cross off the x, you get 1000. So you take a derivative of a function that has a variable just by crossing off the variable. As we go to the next section, you'll understand better why we can just do that. But for now, take my word for it. It's that simple. So now we're going to look at when you have an exponent. Here we have x to the a power. Both x and a are just placeholders, so they're just holding a spot for a number. So to take the derivative of x to some power, you're going to take the exponent and put it in the front, multiply it. Then you're going to subtract 1 from the old exponent to give you your new one. So it's just a times x to the a minus 1. You might not get that right away, but as we go through the examples, it'll become clearer. So here, x cubed. We're going to take this 3, bring it to the front, and multiply. So we're going to get 3x. Now we're going to subtract 1 from this 3 to give us a 2, and that's our new exponent. So x cubed becomes 3x squared. Let's look at this one. 2x to the 4, you're going to bring the 4 to the front and multiply it. So 4 times 2 is 8. Then you're going to subtract 1 from this old exponent to give us 3, a new exponent. So 2x to the 4th becomes 8x cubed. In this case, negative x to the 6th power works the same way. You bring the 6 to the front, multiply it, so you get negative 6x. Then you subtract 1 from the 6 to give you the new exponent. Now, in our next case, it'll explain what we did earlier when we just crossed out the x. So, we're starting with 14x. Now, 14x can also be written as 14x to the 1 power, because anything to the 1 power is itself. So there is an exponent there, it's just hidden. So we're going to use it in this formation. So we'll follow exactly what we did before. We're going to bring the 1 to the front and multiply it. So we're going to get 14, because 1 times 14 is 14. Now our old exponent was 1. We're going to subtract 1 from that, and it's going to give us a 0. Now anything to the 0 power is 1. So it's pretty much 14 times 1. So to review, anything to the 1 power, like x to the 1, is itself. Anything to the 0 power is 1. So this 14x to the 0 is actually 14. So that's why we're able to just cross off the x before to give us 14 as our derivative. In math textbooks, the process I described earlier are illustrated in different ways. So I'm going to show you the common notation you'll see. Students take sometimes weeks trying to see the notation, understand it, see the difference between them, and in reality there is no difference. So I just want to clear that up for you from now. Here we have f of x is our function. To take the derivative, it's going to become f prime of x. This apostrophe is read as prime. So f of x is your function, the derivative is f prime of x. Let's look here. Instead of putting f of x, they just named it y. So y equals 5x. Well, find y prime. We would just do what we did before, cross off the x, so y prime is equal to 5, which is the derivative. With f of x equals 3x, find d by dx. That's how you say this part, d by dx. And that just means the derivative with respect to x. And that's what we've been doing the whole time. So then once again, we just cross off the x. So d by dx of 3x will just be 3. Let's look at here. F of z, whoa, where did that z come from? Well, you can put any variable here because the variable is just a placeholder. So f of z equals 3z cubed. To take the derivative, we do what we always did. Take this 3, multiply it to give us the 9. Subtract 1 from this 3 to give us the 2. So 3z cubed became 9z squared. Now this could be f of z, f of q, f of r, because it's a placeholder. Even this f could change. It could be g of z, g of b, g of d. Whatever it is, you do it the same way. You use the letter they give you and take the derivative with respect to that letter. We have just covered the basics in derivatives. Now, knowing these will give you a strong foundation. So I advise you, if you don't know all of what I did in this video, you should review it. However, if you're comfortable with everything, then I'd move on. Sometimes when you review the video, you just pick up things you didn't see before. And also, on CN Calculus, we'll have plenty of other tips and explanations for the video you just watched. Thank you. Move on.